All right, so now we're going to talk about how to find the slope of a polar function. I've got just sort of a nice simple polar function here, about the simplest you can come up with, r equals theta. You may have looked at that one before. It's a nice spiral graph that we see here. The main thing to keep in mind when we're talking about slope of a polar function is slope is what it's always been. It's dy dx. It's how fast y is changing compared to how fast x is changing. Of course, dy dx is totally different than dr d theta. So finding the slope of a polar function is not as simple as just taking the derivative of this and saying, oh, the derivative of theta is 1, which makes sense because the slope of that graph is clearly changing. And so it wouldn't make sense to have a constant answer. And so how are we going to find dy dx? Well, we basically need to take this polar function and turn it into something that has y and x. And so this goes back to something from the other day where we're converting polar to more rectangular coordinates. And so these two equations will be the keys to finding the derivative. So x is always equal to r cosine theta, y is always equal to r sine theta. And if you want to know where that comes from, it basically comes from SOHCAHTOA once again. And so you've got your little right triangle picture. You've got cosine is adjacent over hypotenuse, sine is opposite over hypotenuse when you solve for x and y. You get that. And so now when we want to find the slope, we're just going to rewrite x as r cosine theta. But of course, in my example, r is super simple. R is just theta. Of course, that could be more complicated. And y is r sine theta. And notice what we have now is basically we have parametric functions. And so in some sense, we don't ever really find the slope of a polar function directly. We just convert it to parametric functions and then use our parametric formula. This time the parameter is theta instead of t, but it's the same idea. So dy dx will be dy d theta over dx d theta, right? Just like before we did dy dt over dx dt. And so we'll just use the product rule every time here. So for dy d theta, we'll do 2 d1 plus 1 d2, and then dx d theta would be 2 d1 plus 1 d2, and remembering that negative in front of the derivative of cosine. And so there's the slope. We can then find the slope at a particular point if we want to know the slope when theta is 9 pi over 4, which would be all the way around the circle and then up here. So we can see sort of a negative, medium negative slope there. We would just plug in that particular value of theta into my derivative equation that I just found, plug it into your calculator, making sure, of course, that you're in radian mode, and you get that slope. There's another video linked here that shows you how to then write the equation of the tangent line, but once you have the slope, you just need to know the point that is happening at that angle, and you write the equation just like normal. Hopefully that went well. As always, let me know if you have questions.